Okay, so I'm going to come back. So in this video we will talk about area of a triangle, and basically this is something that we have done in class 10 chapter. So let me write this down: area of a triangle. So basically we had two ways to find the area of a triangle. First, we knew that basically the area of a triangle is equal to basically is equal to 1/2 times the base times the height, or to say it more, you can say basically 1/2 times the base times the altitude So altitude basically means that, for example, if you have some triangle like this, then basically the altitude of this triangle, if you take this as the base, then the altitude becomes the perpendicular distance from this point to this basically to this base, which means that basically this length is the altitude. Which also means that basically if you have some triangle, for example, something like this, then if this is the base of the triangle, the altitude of the triangle would be basically this distance. So then in this case, the altitude of the triangle would be this. If the triangle is a right triangle, then of course the altitude of the triangle would simply be this side length. This side length would be the altitude of the triangle, and so on and so forth. Now, we had also something in, I think, class 8 or so, which was called the Heron's formula. The Heron's formula gives you basically the area of a triangle based on the side length, meaning that you have the area of the triangle is equal to basically the square root of s times s minus a times s minus b times s minus c, and s is equal to the semi-perimeter of the triangle, if I'm not mistaken. Let me look this up because I'm not really sure if that is correct. So in geometry, it seems that okay. So here we have basically Heron's formula for the area of a triangle, a method for calculating the area of a triangle when you know the length of all the three sides. So you have basically let A, B, and C be the lengths of the sides of the triangle. The area is given by area is equal to the square root of P times P minus A times P minus B times P minus C, where P is the half the perimeter, or in our book it's called the semi-perimeter, if I'm not mistaken, which means that basically S is equal to which means that S is equal to A plus B plus C divided by 2, half of the perimeter of the triangle. So now we knew this about the areas of triangles, and using this we could calculate the areas of triangles. Now in class 10 in analytical geometry, what we learned was that if you have the 3 vertices of a triangle in a coordinate system, basically if you have the 3 vertices of a triangle in a coordinate system, for example, let's call them, for example, x1, y1 and x2, y2 and x3, y3. Then using the 3 coordinates, you can find the area of the triangle as follows. Meaning that if the coordinate system is something like this, you can locate these points. For example, let's call this point, for example, A. Let's call this point, for example, B. And let's call this point C. And I put A over here, and for example, B over here, and for example, C somewhere over here. And I have basically, I call this point A, x1, y1, and I call this point B, x2, y2, and I call this point C, x3, y3. Now suppose that this triangle is in our coordinate system. If I draw these perpendiculars to the x-axis, so this is the x-axis and this is the y-axis, and if I call this point, for example, Q, and if I call this point, for example, P, and if I call this point, for example, R, then basically this ABQP is a trapezium, and also APRC is also a trapezium, and BQRC is also a trapezium. So you can argue that the area of this triangle is basically the area of this trapezium plus the area of this trapezium minus the area of this trapezium down here, right? So you can say that the area of triangle ABC is equal to area of trapezium ABPQ or ABQP, trapezium ABQP plus the area of the trapezium APRC, and once you add the two together, if you subtract from that the area of the trapezium BQRC minus the area of trapezium BQRC, BQRC. And one more thing that we know is that basically the area of a trapezium, you know that the area of a trapezium is equal to 1/2 times sum of the parallel sides times the distance between them. Meaning that if you have a trapezium, something like this, the area of this trapezium, if I call this length A and this length B, and if I call this length H, for example, then the area of this trapezium would be basically 1/2 times A plus B, sum of the parallel sides, times the distance between them, which is H. That is the area of this trapezium here. So now we can use all of the information that we have here in order to find the area of this triangle here, because it's the area. You can simply calculate the area of this trapezium plus the area of this trapezium, and then you can calculate the area of this trapezium, and then based on that, the area of the triangle ABC can be found. Now, so the area of trapezium ABPQ or ABQP, this trapezium here, these two are the parallel sides, and so I can write the area of, I'll write this in another color. So you can write basically the area of triangle ABC. Triangle ABC is equal to the area of the trapezium ABQP, which is basically 1/2 times basically this side length plus this side length, which is BQ plus AP. BQ plus AP times the distance between them, which is QP. That is the area of this trapezium. And the area of this trapezium APRC is basically 1/2 times the side length, which is AP plus CR. AP plus CR times the distance between them, which is PR. And minus this trapezium here, and in this trapezium basically the parallel sides are BQ and CR, so I can write negative 1/2 BQ plus CR times the distance between them, which is QR. Now, I can basically write these in terms of x1, y1, and so on and so forth, meaning that I can write 1/2. This one I can write 1/2 BQ plus AP. BQ plus AP would be basically so BQ is basically this height, which is y2. AP is basically this height, which is y1. So I can write this as y2 plus y1 and times basically QP, which is basically the distance between x2 and x1. So I can write it as, for example, x1 minus x2. I can write it as x1 minus x2. x1 minus x2. So you see over here, this distance is basically x1, and this distance is x2, and this distance therefore would be x1 minus x2. This distance over here would be x1 minus x2. x1 minus x2. And by the same logic, you can find that you can write this as 1/2 times AP plus CR. So AP is y1, CR is y3, y1 plus y3, and PR would be basically the distance between basically x3 and x1. So this point over here is x3, and so I can write this as this distance over here is x3, and this distance over here is x1, right? So that means that this distance here would be x3 minus x1. x3 minus x1. And then from that you need to subtract 1/2 times BQ plus CR. So BQ is basically this BQ, which is this height, which is y2, and CR is basically CR. Okay, so this distance over here is y3, so that's y2 plus y3, and QR is basically this distance here, which is actually the distance between x2 and x3, right? So I can write this as I can write this distance up to here is basically x3, and this distance over here is x2, so that is x3 minus x2. x3 minus x2. So then what I can do is that I can rewrite this as y2 plus y1, x1 minus x2, and y1 plus y3, and y2 plus y3, and x3 minus x2, okay. So now what you can do is that, for example, you can write now let me see how they have written this. I don't really understand. Okay, so this basically needs a little bit of algebra, but essentially with a little bit of algebra you can actually derive the formula, meaning that you need to multiply, and then there are some common terms that you can cancel out, and then you will get to the area. So if I take this 1/2 out from these terms, I will get basically 1/2 times I will get 1 by 2 times basically y2 plus y1 times x1 minus x2 plus y1 plus y3 times x3 minus x1 minus y2 plus y3 times x3 minus x2, right? And let me check here, y2 plus y1 times x1 minus x2 plus y1 plus y3 times x3 minus x1 minus y2 plus y3 times x3 minus x2. Okay. And then what you can do is that just simply multiply, meaning that you will get basically 1/2 times basically y2 x1 minus y2 x2 plus y1 x1 minus y1 x2, and then multiplying these you will get plus y1 x3 minus y1 x1 plus y3 x3 minus y3 x1, and then over here you will get minus, because this negative is multiplied by everything, so you will get minus, so let me write this down here. You will get minus basically y2 x3 minus y2 x2 plus y3 x3 minus y3 x2, and then you can write this as 1/2 of basically y2 x1 minus y2 x2 plus y1 x1 minus y1 x2 plus y1 x3 minus y1 x1 plus y3 x3 minus y3 x1, and then multiplying this negative sign by all of these terms, you'll get negative y2 x3 plus y2 x2 minus y3 x3 plus y3 x2. So then there are some of these terms that you can cancel out, for example y2 x1 and so for example this one you cannot cancel out, this remains y2 x2 and y2 x2 you can cancel out, this is negative, this is positive, you can cancel these two out. y1 x1 and negative y1 x1 you can cancel out, and y1 x2 you cannot cancel that out. y1 x3 you cannot cancel that out. y3 x3 you can cancel that out, and you have basically y3 x1 y3 x1 you cannot cancel that out, this is 1. y2 x3 you cannot cancel that out, so 1 2 3 4 5 6, and y3 x2, so these basically remain. And then what you can do is that you can, for example, from between basically this term and, for example, this term, you have x1 here, so you can write it as 1/2 times basically x1 times y2 minus y3, and so these two are taken care of. And then you have x2 over here, which means that you can write x2 and then you can write y3 minus y1, and then you can cancel that out, and then you have x3 over here times basically y1 minus y2, and that becomes the, so you have 1/2 x1 x2 x3, and then y2 minus y3 y3 minus y1 y1 minus y2. That is the area of the triangle. That is the area of the triangle with vertices basically x1 y1 and x2 y2 and x3 y3. So now what they have done is that they have written this this formula in form of a determinant. So they have basically this expression. This expression can be written as follows. So you can write this as delta is equal to 1/2 times the determinant x1, y1 and x1, x2 and x3, and y1, y2 and y3, and 1, 1, 1. Now it seems that it actually works no matter how you expand this. I don't really know how they have done this. But it seems that it does actually work. Meaning that we can actually take some example. For example, let's say that actually it would be fun to take a couple of points and then use the distance for, but we don't have time for that. But let's say that, for example, you have some triangle, and basically the vertices of the triangle are 3, 8 and -4, 2, and for example 5, 1. And this triangle would be some triangle like this. So you have 3, 8 would be 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. So you would have basically this point over here. -4, 2 would be 1, 2, 3, and 4. And this point over here. And 5, 1 would be 3, 4, 5. And 5, 1 would be this point over here, and then you would have a triangle like this. So now the area of this triangle, you can calculate it using the formula that you have, meaning that you can say that these are the points, that the vertices of the triangle. You can say that the area is equal to basically 1/2 times x1 times something plus x2 times something else plus x3 times something else. And then this becomes, now I forgot to tell you, you see over here you have 3 points related to the vertices of this triangle, which are x1, y1, and you have x2, y2. I think I already told you this. And x3, y3, right? So for these 3 points that we have to write in the parentheses, you start from, it's just like a circle, meaning that you start from y2 and y3, so you write it as y2 minus y3. This is just to remember the formula. And y2 minus y3, and then you have to go in circle to basically from this you will move to y1, so y3 minus y1, y3 minus y1, and then you have to complete the circle by going from y1 to y2, and then you have a complete circle, y1 minus y2, and that is now exactly the same as the formula that we had here, right? Now, what that means is that now what we can do is that we can calculate the area of this triangle, which is basically this is equal to 1/2 times, now take this as 0.1, for example, 0.2 and 0.3, meaning that this becomes x1, y1, x2, y2, x3, y3, right? Now, x1 is 3, and y2 minus y3 would be basically 2 minus 1. And x2 is -4, and y3 minus y1 would be 1 minus 8. And x3 is basically 5, and y1 minus y2 would be 8 minus 2. And then if you calculate this, you will get 1/2 times, for example, 2 minus 1 is equal to 1, so that's a 3. 1 minus it is -7. -7 times -4 is equal to positive 28. And 8 minus 2 is equal to 6. 6 times 1 is equal to 30. So this is equal to 1/2 times 58 plus 3 is equal to 61. 61, which is equal to 61/2 square units, right? 61/2. Now let's do the same thing. So using the formula, I got 61/2 square units. Now let's use the formula and actually the determinant, and see what we get with the determinant. So using the determinant, what I will get is I would have to expand the determinant as this determinant as basically delta is equal to 1/2 times this determinant. So you have 3, -4 and 5, and 8 to 1, and 1, 1, 1. Now I want to expand this determinant along at least, for example, row 1 and column 1, and see what we will get. Now expanding along row 1, we have basically delta is equal to 1/2 times basically -1 raised to the second power times 3 times this determinant 2, 1, 1, 1, 1, which is 2 times 1 is equal to 2 minus 1, which is equal to 1. And then plus -1 raised to the third power times 8 times this determinant, which is -4, 1, 5, 1, which is -4 minus 5, which is equal to -9. And then you have plus -1 raised to the fourth power times 1 times this determinant, which is -4 minus 10, which is equal to -14. Right? And calculating this, I will get 1/2 times, basically this is +1, so that's just a 3. And this is -1, -1 times -1 is equal to +1, so 72. And this is a -14. And 72 plus 3 is 75. 75 minus minus 14 is equal to 61, so that's 61 halves square units, which is correct. It works. It actually does work. Now, if I expand this along along C1, for example, if I expand this along C1, let's see what we get if we expand it along C1. Along column 1, we get, along this column, I have delta is equal to 1/2 times negative 1 raised to the second power times 3 times basically times this determinant, 2, 1, 1, 1. And you have 2 minus 1, which is equal to 1. Plus negative 1 raised to the, so here you have the second row first column, so to the third power, times negative 4, times basically 8, 1, 1, 1. 8, 1, 1, 1, so you have 8 minus 1, so that's a 7, and plus negative 1 raised to the fourth power times 5, times this determinant 8, 1, 2, 1, which is basically 8 minus 2, which is equal to 6. Which is equal to 6. Now, if I calculate this, let's see what we get. I have 1/2 times, basically this is 1 times 1, so that's a 3, and then you have negative 1 times negative 1 is positive 1, that's 28, and here I have 1, and that's a 30, that's 58 plus 3 is equal to 61, and that's 61 halves. It actually does work. I was actually not sure that it would work. And that shows that I have a little bit of, that shows that I might have, or I do have a little bit of problem with these, determining that I don't actually, see how they work in my mind, so it probably takes a little bit of more. I do understand that if you expand the determinant any way that you want, that you will have the same value. But then how you set up that determinant is of course important, and well, they have set up the determinant this way, and it actually does work. Anyway, now there is one thing there is basically a couple of remarks here that we need to take care of, and then do a couple of examples. So, remark number one. Remark number one, we have, since the area is a positive quantity, we always take the absolute value of the determinant. So this determinant, if it gives you a negative value, you have to actually take the absolute value of that value, because sometimes it gives you a negative value, and of course area cannot be a negative value. That you already know, hopefully. And number two, if area is given, use both positive and negative values of the determinant for calculation. Meaning that sometimes what happens is that, for example, let's say that you have this vertical, this slanted line, and you have some point over here, some point over here, and if I take some point over here and connect them together, I'll get a triangle, right? So this triangle has some area. For example, let's call it A square units. Now, if you, I'm saying it has so much area. if you, for example, use this formula. Now, if I take the image of this point with respect to this line, which is hopefully this line over here, so somewhere over here, and if I connect these points together, you see that I get another triangle of the exact same area on the other side of this line. And of course the area of this triangle is equal to the area of this triangle. But sometimes what happens is that if you put the coordinates of this triangle below in basically in this formula, that the formula will give you a negative value. And then if you put the coordinates of these 3 points of the triangle on the upper side of the line into the formula, you will get the same magnitude, a number with the same magnitude, but with a positive value. Meaning that for any magnitude, you might actually get 2 possible triangles, and that means that basically when the value of the determinant is given, you have to basically take the number as negative and also as positive, and that give you possibly 2 sets of x and y's, for example. So that's basically what I think most probably is meant by this statement. And of course, you know that the area of basically 3 collinear lines, 3 collinear points is 0. Meaning that if you have, for example, and that's actually one of the tests that we used to use in that chapter, that we used basically, they give you basically 3 points, for example, A, B, and C, and you want to show that these three points are collinear. If the 3 points are collinear, and if you put these 3 points in this formula, the area of the triangle becomes 0, which means that the points are collinear, right? So that's basically that. Now there is something interesting here that I would like to think about a little bit, but let me actually take a few minutes rest and I'll be back with these 3 collinear points. Okay, so now there is something interesting based on, now this is of course based on the collinearity of these, of the points that you have, and based on based on the properties of determinants that we have already talked about in this chapter. So first of all, if three points, basically A, B, and C, are collinear, so what that means is that they are collinear, meaning that they are on the same line, on a straight line. And since they are on a straight line, you can imagine that they are the 3 vertices of a triangle with basically with height 0. And for example, you can imagine that the base of this triangle is from here, from this point all the way up to this point. This is your base length, and your height is 0, because the third point is on the base. And since you know that the area of a triangle is equal to 1 times the base times the height, when your height is equal to 0, the whole thing goes to 0, and so basically the area of the triangle becomes 0. And of course, if you have 3 such points where basically the points are collinear, if you put them in this formula, of course the area will come out as 0. So that you already understand. Now, what we have done here is that we have developed this determinant, and using this determinant, we are actually doing the same thing that we are doing in the same thing as we are doing in this formula. Now, if A, B, and C are collinear, there are basically 3 possible cases, not more than that. Either the 3 points are on a, number 1, on a horizontal line, or the 3 points are on a vertical line, or they are on a basically slanted line, right? So what that means, if the 3 points are on a horizontal line, that means that then basically you have the 3 points on this line, and you can see that the y coordinates of all of these 3 points are the same. That means that y1 is equal to y2 is equal to y3. So that means that I can write this determinant as, for example, for case 1, I can write this determinant as delta is equal to 1/2 times, for example, x1, x2, x3 having 3 different values, and y1, y2, y3 are just some value equal to some k, for example, and you have 1, 1, 1 over here, and you can see that the two, basically column 2 and column 3 of this determinant are in the same ratio of k to 1 or 1 to k, and therefore, based on the properties of the determinants, we said that if basically 2 rows or 2 columns of a determinant are in the same ratio, then the value of that determinant is equal to 0. Because what I can do is that using this, basically if I want to evaluate this determinant, I could simply write it as delta is equal to 1/2 and take this k out times k, and then write this as x1, x2, x3, and taking this k out, I will be left with 1, 1, 1 and 1, 1, 1, and now basically these 2 columns are exactly identical. That means that this is equal to 1/2 times k times 0, which is equal to 0. And therefore, if you have 3 collinear lines, those 3 collinear lines would correspond to a triangle with area 0 square units, right? So this is the case 1. Now in case 2, suppose that you have your points on a vertical line. On a vertical line, you would have some situation like this. And you can see that the x coordinate of all of these points are exactly the same if they are in some coordinate system. The x coordinate of all of these would be equal to x1. So then that means that I can write this as all of these x coordinates are the same. Then that means that the determinant becomes 1/2 times basically some k, for example, k, and k, and y1, y2, and y3, and 1, and 1, and 1. And then what I can do, I can take this k out, so that's k divided by 2 times 1, 1, 1, y1, y2, and y3, and 1, 1, 1. And then you can see that these 2 columns are exactly identical. That means that this is equal to k divided by 2 times 0, which is equal to 0. Which means that 3 points on a vertical line would correspond to a triangle with area 0, right? Now, basically the case 3 of this is also interesting, because, for example, suppose that this is your coordinate system and this is any line with any sort of slope, negative or positive. When you have a line, there is basically a relationship between x's and y's, meaning that, for example, when I say that, for example, when I draw the graph of the function y is equal to x, that would be a 45-degree line. That would be a 45-degree line. Now, what that means is that any point that I pick on this line, the x coordinate of this point, this would be x1 and this would be y1. x1 would be equal to y1. And x2, for example, would be equal to y2 all the way up to x of n is equal to y of n. Meaning that you can just keep going all the way up to positive infinity, all the way up to negative infinity. This relationship is going to be there. If on the other hand I have a line, for example, suppose that this is 1 unit and this is 2 units, and suppose that I have this line over here, and this is y is equal to 2x. Now what that means is that if whatever point I take on this line, the x coordinate of that point is half the y coordinate of the same point. Meaning that if x is equal to 1, y is equal to 2. If x is equal to 2, y is equal to 4. Always the x coordinate is half times the y coordinate. Which means that there is always this relationship between x and y when it comes to, and that relationship of course remains constant because it's a linear function. If it was some function that was changing over time, for example, like a periodic function that or a polynomial, for example, then it would be different. You couldn't probably find any rules for that. But when it comes to a line, to a straight line, this relationship is always there. Always, 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 your x coordinate is half the magnitude of the x coordinate is half the magnitude of the y coordinate. Now, what this means is that when the points are on a slanted line, there is basically the x and y's are always in the same proportion. And in the properties of determinants, we said that if 2 rows or 2 columns of a determinant are proportional or in the same ratio, then the value of that determinant is equal to 0, right? Which means that, and that is exactly the case here, because if suppose that, for example, all of the 3 points are on the line y is equal to 2x, then there is always this relationship between x and y, and what that means is that my delta becomes, for example, 1/2 of, for example, this determinant, for example, the x1 is equal to, I can write basically the x1 is half of y1, which means that if I take this as a, this becomes 2a. And this again, if I take this as b, this becomes 2b. If I take this as c, this becomes 2c, and so on and so forth. And you have 1, 1, and 1 over here. And what that means is that now all of the corresponding elements of the first column and the second column of this determinant are in the same ratio, and therefore you can say that of course this, you can basically write this as 1/2 times, for example, you can write this as, for example, a, b, and c, and take this 2 out, write it times 2, and this becomes a, b, and c. and this becomes 1, 1, and 1. And then again, you are left with the same situation that basically two of your columns are identical, and the value of this determinant becomes 0. So this is 2 halves, which is equal to 1 times 0, which is equal to 0, right? So this is something interesting that basically connects analytical geometry to basically matrix and determinant algebra. And with all of that out of the way, we have 2 examples here that we will solve, and then we will end this video. Okay, so now let's find the example number 17. Example number 17, we have, you want to find the area of the triangle whose vertices are 3, 8 and -4, 2 and 5, 1. And I already did this as I was going through the concept, and I think this was 61 by 2 square units. Let's see what we get. It's actually the same thing. So the determinant, you have to write it as delta is equal to 1/2 times basically x1, x2, x3, and y1, y2, y3, and you have 1, 1, 1 over here, right? So this becomes, for example, you can take this point as 1, take this point as 2, take this point as 3. And then this becomes x1, y1, x2, y2, x3, y3. And therefore, delta would be equal to 1/2 times the determinant x1, x1, x2, x3, 3, -4, 5, 3, -4, 5, and 8, 2, 1, 8, 2, 1, and 1, 1, 1. And so you have 1/2 times, now you can do, for example, we cannot really simplify this. I mean, there is nothing that can be divided or subtracted or anything like that as far as I can see, although I'm not really good at that. So but well, you can write this as expanding along the first row. You can write it as 1/2 times, for example, -1 times raised to the second power times 3 as basically times this determinant, which is 2 minus 1, plus -1 to the third times 8, and then you have -4 minus 5, plus -1 to the fourth times 1, and then you have -4 minus 10, and then you have basically 1/2 times, so this is 1 and this is 2, 2 minus 1 is equal to 1, so you'll get a 3 over here. So that's a -9 times -1 is +9, 9 times 8 is equal to 72, and over here you have 1 times 1 is equal to 1, that's -14. And so you have 75 minus 14, which is equal to basically 61. It's equal to 1/2 times 61, which is equal to 61/2 square units. So that was question number 17. Now question number 18. Question number 18, we have find the equation of the line joining joining A and B. Find the equation of the line joining A with coordinates basically 1, 3 and B with coordinates 0, 0 using determinants. And find K if D find D, and no, I was actually right, I'm sorry. And find K if basically D with coordinates K, 0 is a point such that area of a triangle is 3 square units. Is a point such that that area of the triangle ABD, such that the area of triangle ABD is 3 square units. Okay, so what you can do is that since these basically the solution would be basically, since these two are collinear, since A 1, 3 and B 0, 0 are collinear, basically, so you want to basically find the equation of the line joining these 2 points, meaning that these 2 points are both basically on a line with some equation, right? So that means that on that line you have this point, and you have an infinite number of points. So which means that another point on that line, and I need to rephrase my statement. I would say that since we are looking for the equation of the line, joining A and B, we can assume that some point P, for example, with coordinates x and y is also on the line, or you can say lies also on the line. Therefore, the points A, B, and P are collinear. Now, so the area of a triangle formed from those vertices would be 0. So we have, so now basically we can use we have basically now delta is equal to 0 because the area of that triangle is equal to 0, and the points that we have are A, B, and P. So A is basically, the coordinates of A are 1, 3, the coordinates of B are 0, 0, and the coordinate of P are x, y. And now I can use basically the determinant that we had, that was delta is equal to 1/2 times the determinant x1, x2, x3, and y1, y2, y3, and 1, 1, 1. And so then I can take this as 0.1, take this as 0.2, take this as 0.3, and I know that my delta is equal to 0, so I can write 0 is equal to 1/2 times basically x1, y1 would be basically 1 and 3, x2, y2 would be 0 and 0, and x3, y3 would be x and y, and that would be 1 and 1. And then I can solve this basically determinant. Now if I expand along the second row, expanding along the second row, we have, so this is 0, 0, and 0, and so you have basically the value of the determinant would be 1/2 times basically -1 raised to the, so you have in the second row, third column, so to the 5th power, and times 1, and then eliminating this column and this row, you would have this determinant y3xy, which would be basically y minus 3x, and so this would be equal to 0, which means that basically this is -1 times this, which is equal to 1/2 times, and -1 times this would be equal to 3x minus y is equal to 0, which means that basically 3/2 x minus 1/2 y or let me actually multiply both sides by 2. I will get 3x minus y is equal to 0, which means that negative y is equal to -3x, which means that y is equal to 3x. And that is the equation of the line. Now, that is the equation of the line joining those 2 points A and B, right? Now, the second part of this question is basically if you want to find K, so the points are A was basically 1, 3, and B was basically 0, 0, and we said that basically if you want to find K if D is a point with coordinates K, 0, is a point such that the area of the triangle, area is written as AR, I suppose, of triangle ABD is equal to 3 square units. 3 square units. 3 square units, right? So if you have basically this point A, point B, and point D, and the area of this triangle becomes 3 square units, then you can take this as point 1, point 2, and point 3, and write delta is equal to 1/2 times basically x1, y1, x2, y2, and x3, y3, and you have a bunch of ones over here, and then you can write this as, so the delta becomes 3 square units is equal to 1/2 times the determinant, basically 1, 3, and 0, 0, and k0, and 1, 1, 1, and so you can expand along the second row, along R2 we have, so basically you have 3 is equal to 1/2 times basically -1 raised to the, so you're in the second row, third column, so to the 5th power, times 1, times, then eliminating this row and this column, you'll be left with 1, 3, k0, which is basically 1 times 0 is equal to 0, -3k, -3k, and so you have -1 times -3k is +3k, so 3 is equal to 1/2 times 3k, and 3 you can cancel out, so 1/2 k is equal to 0, 1/2 k is equal to 0, which means that k is equal to 0. So that means that if you take k as 0, then which doesn't make any sense actually. No, that doesn't make any sense. So 1, 3, 1, 0, 0, 1 and k01, I think I have made a mistake here. So let me see, because if k is equal to 0, then this becomes 0, 0, and then that would be again the same point as this point, so you wouldn't get any triangle. You wouldn't get any triangle, meaning that the area would actually be equal to 0, and it wouldn't be equal to 3 square units. That's the problem. That's why I said it doesn't make any, and it doesn't really make any sense, because k can be plus or minus equal to, as I can see over here. Now, if I expand along the second row, I have 3 is equal to 1/2, so -1 times -1 raised to the power 2 plus 3 is equal to 5 times 1 times 1 times, so that is actually correct. Oh, that's not a 0, that's a 3. So let me see, 3 is equal to basically 1/2 times, that's 3k, 1/2 times 3k, or 3/2 k basically, 3/2 k, if I multiply by a 2, I will get 6 is equal to 3k. That means that k is equal to 2, right? So this is one of the possible values. Of course, you can, or you should, actually take this as -3 as well, because that gives you another triangle. Which means that I can write this as -3 is equal to 3/2 k, which gives me basically times 2 is equal to -6 is equal to 3k, which gives me k is equal to -2. Right, so which means that basically based on these two, I can say that k is equal to ±2. That is actually the correct answer here, right? Okay. Now, next we have only 5 exercises, and then we will talk about minors and cofactors. So I'll see you in the next video with the exercises, and thank you.